We are now going to look at what kind of shapes molecules take. And we're going to start by looking at balloons. And we looked at that balloon shapes lab together, and that should give you a really good idea as to how all these molecules are starting to look. So if you've ever rubbed two balloons in your hair to create a static charge on them, you try and bring the two balloons together, what they do is they have like charges, so they want to repel. So they want to move as far away from one another as they possibly can. Well, molecular shapes are the same way, because we have all these electrons around everything that are repelling one another. Remember, like charges repel. So if we look at what's called VSEPR, VSEPR just stands for valence, shell, electron, pair, repulsion. So the big thing we're looking at here is electron pairs that are repelling. And which electron pairs? The ones in the valence shell. And what this is it's an arrangement of atoms that minimizes the repulsion of the electrons. So molecules will take these shapes that minimizes the repulsions between electrons. So not too close, but not too far away as well. They have these special angles they sit at, and they have these special shapes that they take. So let's continue with this balloon example. Okay, and with the balloon shape lab, we made some of these different shapes. Okay, and balloons will take the shape that minimizes the interaction between the two if they are like charged. So on this one, we have what's called a linear. Okay, where these two here are 180 degrees apart. So that's as far apart as these two can get between here. They have 180 degrees. Here, we're looking at 3 now, so they can't quite get that far apart, so they get something closer to like 120 degrees. All right. And when we get to 4 atoms in a molecule, or around a center molecule, we run into some problems, because 120 is not going to work. Okay, and if I try and write it so that I have something in the middle, and then 1, 2, 3, 4, like flat, these are all 90, all right, but we have to remember that we have 3 dimensions. So we can actually get a little further apart than 90, and we end up with this kind of tripod on the bottom, okay, and then one that sticks up on top. But it's really hard to draw this because they're not all on the same plane. So if you're an artist, it's a little bit easier. You can use some shading and things like that. But for chemistry, we don't. We have other special symbols that we looked at in the balloon shape lab, and that we'll look at here in a minute. We also have one now, okay, that has 6 things around it. And now we're back to, okay, I can't get any farther apart than 90. But we have to have 6 things to get 90 degrees, not just 4. They're not flat. Okay, molecules take up a 3-dimensional space because they are 3-dimensional. You're not a flat human being. You're made up of molecules that are 3-dimensional, so you are 3-dimensional. Okay. All right, so then we're going to look at what are called electron pairs. Well, electron pairs work just like balloons, okay, and then they repel one another. And when they repel one another, this causes the atoms to be positioned at fixed angles. We call these fixed angles a bond angle. A bond angle is the angle between the center atom and 2 terminal or end atoms. When we look at bond angles, we have to be careful because lone pairs occupy a larger space than bonded pairs. So what happens is these lone pairs will push down and actually push the bonded pairs closer together. Let's take a look at now what these different shapes names are. And I mentioned a couple of them before. Okay. Now if we have BCl2, BCl2 has 2 shared pairs, which means that it has a center atom connected to 2 things. There are no lone pairs. We don't care about this column. Its name is called linear, and they're 180 degrees apart. Now if I go to 3 total pairs, 3 of them shared with no lone pairs, that means I have no lone pairs around my center. I end up with what's called trigonal planar. planar because it's flat. It's in one plane. And they have 120 degrees between each one. When I go to look at 4, okay, you have a couple of different options. You actually have these 3 different options here. Okay, I can have tetrahedral, which has 4 shared pairs and no lone pairs on my center. That's 109 degrees with a tripod on the bottom and the one sticking up top. Now, if I still have 4 things around my center, but I have 3 atoms and 1 lone pair, and I end up with what's called trigonal pyramidal. And those are 107.3 degrees. Because this lone pair up top pushes all of these atoms closer together. So it's not 109 anymore, but 107.3. Let me go to water, where I have 2 shared pairs, 2 lone pairs, and I end up with 2 lone pairs pushing them closer together. I end up with 104.5 degrees. Let me get into the ones that have more than 4, okay, and 5 and 6 atoms around them. We end up with, this one actually has 2 bond angles because it has 3 around the center, which are 120, and the top to the side and the bottom to the side are 90. We call that trigonal bipyramidal because you make 2 pyramids, one on the top, okay, and one on the bottom. Then we end up with octahedral, which is 6 atoms and no lone pairs, and those are all 90 degrees. So this is the one in your notes. We're given one that looks more like this, okay, which has not necessarily the nice pictures, but has the chemistry diagrams, okay, which is how you should draw all of these molecular shapes. So a Lewis structure can have any arrangement. Okay, I could draw this trigonal planar as a Lewis structure, as a middle atom and 3 things around it. Okay, but if I'm going to draw the molecular shape, I have to draw it with these 3 at 120 degrees. Now, if I look at the tetrahedral, that's where I have to start and putting one that's sticking out front with a triangle, and the little dash line that goes back into the page. Okay, and these are the 109.5. Then we have the 1 lone pair, which makes these 107.3. And then we have 2 lone pairs, which makes it 104.5. You have tetrahedral, trigonal pyramidal, and bent. All of these names and the number of lone pairs and the atoms are on the back of your periodic table, but these nice little pictures are not. When we get to 5, okay, you have 4 different options. We can add numbers of lone pairs. Well, the first one is going to be the 90 degrees from top to the side, and 120 as it goes around the middle. And then we have varying degrees of that. That one I do not make you know. If I look at then octahedral, which has 6, you've got 3 of those that are going to be on there. Okay, with 1, 2, or 3 lone pairs, these are all 90. Okay, and then there'll be a little bit less as we go down there. Those are all the names for the different shapes that you will see. And you are going to have to know what these shapes look like. So let's determine the molecular shape and the bond angle for each molecule. So when we do these, the first thing we have to do is look at the Lewis structure. Okay? So I've got BF3. Count up your electrons. Boron is 3. Fluorine is 7. 7 times 3, I make 24 total. Okay? So I would take B in the middle. I would have F, 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 and put all my lone pairs. Remember, boron's one of those exceptions where it only wants 6. Has that suboctet. So then I count my dots. 8 here, 16, 24. So look at your chart. Boron, okay, has 1 center, 3 things around. That's my trigonal planar. And instead of being straight across, I'm going to get them as far apart as I can. So it's going to look like B, and F's kind of kicked out. And then you still put all your lone pairs on. And your bond angle, 120 degrees. If you look at the next one, which is BEF2, we're going to add up. Beryllium is 2. Fluorine is going to be 14 total for 6. So I'll put BE in the middle, F on each side, Let me add our electrons around. Well, this is technically an ionic bond, but it's one of the easiest ways to show this bond angle. Okay, and you can draw Lewis structures for ionic bonds. Okay, we don't do that very often, but again, this is just the best example, so just kind of bear with me. Well, this one's easy. It's connected to two things, so this is called linear. So it really just has the same shape, and they are 180 degrees apart. All right, if I look at the next one, which is OCl2, I add up. We have oxygen, which is 6, 2 chlorines, which is 14, so I have 20. I'm going to have O, Cl, Cl, add all of our lone pairs, give everything 8, see if that's 20 or not. I've got 8 here, 10, 12, 14, 16, 18, 20, so I've got 20, so that's good. Now, it's not the same as the linear, even though it might look like it, because this O has 2 lone pairs and 2 atoms. So I'm looking at a total of 4 things around my center atom, which makes it a tetrahedral type design. Okay, so I look in that 4th group here, the things that have 4, and I find the thing that has 2 lone pairs and 2 atoms, which is this one right here, and that is our bent shape. So I go O, lone pair, 1 in the front, 1 going to the back, chlorine, chlorine, with all the lone pairs. Like I said, that is called bent, and those are 104.5. All right, let's try the last one, CF4. Carbon is 4, fluorine is 7 times 4, which is 28. It's going to be 32. Carbon in the middle, 4 fluorines. And that'll be my 32. So this is what we call tetrahedral, because there are 4 things connected to my center, and they're all atoms. We call that tetrahedral. So it'll look very similar to this one that's bent up here, except for that they're all going to be atoms. So I go up top, 1 kicked out to the bottom of my triangle, okay, which kicks out to the front, and the one going behind, like my little tripod. So I have F, 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 and all your lone pairs, and then that one will be tetrahedral. Let's answer the last 2 questions. What is a bond angle? Okay, the bond angle, like I said earlier, is the angle formed by 2 terminal atoms in the center. How does the presence of a lone pair affect the spacing of bond orbitals, which means the spacing of the bonded pairs? Okay, the lone pairs take up more space and push them together. So anything with a lone pair is going to have a smaller bond angle.